And we are going to start sharing screen. Oh, no, not the. Okay, so today we will start with a new topic. So we move quite fast, okay. And so what this in this unit we will learn is about dimensionality reduction, okay. And if you recall previously in decision tree and the random forest, in that unit, we also learned that with decision tree and a random forest, you can pick the feature importance. And the last class example also shows is that with the feature importance, and sometimes you can filter out some features, is it? So that's kind of part of feature reduction that we call it feature selection. Feature selection. Basically, it's in machine learning part of not a feature machine feature engineering. This is also part of data analytics and machine learning. Okay. Itself is also a topic, and with feature and feature selection is part of it. And if you recall, also previously that we also learned the SVM. Is it SVM is about linear. Then we for nonlinear. If you recall, we can use the kernel trick, is a kernel SVM, but that's opposite of feature selection. Feature says you reduce some features, is it? With the kernel trick, then you kind of increase the dimension, increase the dimension, is it? Then because once you have high dimension space, is it? Then we can do linear separable. So that's all regarding anyway, increase dimension or decrease dimension. So what in this unit we will discuss is dimensionality reduction. Oh yes, if you recall, the other one is about that L1. Is it that if you recall the regularization, is it? And we have L2 regularization. But remember, L2 regularization is you're going to add the weight. So manually add weight impact. So basically here is a bias. Is it some bias? But if you recall with L1, we can do dimension, we can do reduce feature, is it? So dimension reduction. Is it because if you recall that, so the contour, is it? And with dimension, with L1, then it's a diamond shape, is it? Then, so this is W1, this is W2, then you can reduce because we find the intersection part of the contour and the L1, is it? And then in this case, then the L1's impact is 0 because you pick this point. So there's kind of, you reduce feature 1's impact. we can ignore that based on that. Then you pick like a feature 2, okay? So that's also we already learned. So we will learn some new ideas here, okay? And also regarding previously, if for feature selection, if you recall, for feature selection, we maintain the original features. Is it? We didn't change the original features. Is it? But if you recall, for kernel trick, then is you manually add some features. Is it? But anyway, for feature selection, we maintain original features. Okay, this doesn't mean we do the feature scaling. Okay, so feature scaling has nothing to do with. That's a different story. Okay. So anyway, so we maintain original feature because later on when we say today there's another technique, then basically we are not going to maintain the original feature, okay? And there is another concept in feature engineering is called feature extraction. Okay, so this time it's extraction. So this extraction, then this time it's involved, we project or we say transform. So it's some math techniques behind it. Kind of like the kernel. The kernel is you bring low dimension to high dimension, is it? From plain 2 dimension into 3 dimension, is it? And what over here is we are going to try and project. And for kernel tree, you also do projection, is it? And over here is we project data onto new feature space. Okay, new feature space. But this time we are going to, because this time it's in the context of dimensionality reduction, not like increasing the reduction. Then it says the feature extraction can be understood as approach to data compression. So later on we will see it's kind of like can also serve as data compression, okay? But whenever you compress data, but there is a goal that we need to maintain most relevant information, okay? Maintain the relevant information. And data compression, used a lot. Is it like image, video, audio? Is it like even we do zip? Is it all those data compression? Is it? It's some math behind it, and you can still recover that. It's not like after you compression, you will not be able to recover that. Is it? And I believe we, if you recall, we also discussed that MNIST example, if you recall. And for that example, we can also, filter out some of the features. Is it? It's just those digits, the definition is not that high, but they are still recognizable. Is it? So that's also kind of the concept of dimensionality reduction, okay? And over here, so what today we will learn, you will also see it can kind of also serve like a data compression, okay? And over here it says a feature extraction. And of course, its purpose is not just used to, and of course it can improve storage space. Is it? Because you compress, you reduce dimensionality. Is it? And you can also improve the computational efficiency. Is it? So we can also improve. It can also improve predictive performance. Okay. That by reducing the curse of dimensionality, if you recall previously, we learned the curse of dimensionality, then we can reduce the dimensionality, okay? As I said, especially sometimes your model cannot be regularized. Is it? Then, because if you recall, L2 regularization is not applicable to all models. So sometimes if it's not, then what can we do? Okay. So keep that in mind. Data selection, not that, feature selection and the feature extraction. Okay, the concept. So feature selection, it's reduce the dimensionality. Okay, and the feature selection or feature extraction. Extraction is an alternative approach for feature selection. Okay, so the purpose is also dimensionality reduction. And of course, it can also save space, etc. Okay, and over here, the feature extraction. Feature extraction then is going to transform the data onto a new feature subspace of lower dimensionality. Okay, not like a kernel. Kernel is to transform into higher dimensionality. Okay, so here extraction is to convert it to lower dimensionality. So what today we will learn, these are also quite useful algorithms, okay, in machine learning. One is the techniques we will learn is PCA. So PCA is called principal component analysis. So there's some math background. It's also quite comprehensive, okay, for the math background. And also for PCA, keep this in mind, it's for unsupervised data compression. Okay, so it's not mean that the data must be classified, already have tagged, is it? So it's unsupervised. Okay, and it says most prominently for feature extraction and dimensionality reduction. So this PCA in machine learning is a quite a large topic. Okay, there are a lot of discussions and also research on it. Okay, but right now it's already quite mature, but back decades ago. Okay. So anyway, so PCA, remember, it's for unsupervised feature extraction, okay, to do dimensionality reduction. And the second one we will learn is called LDA. So it's a linear discriminant analysis, but this one is for supervised. Okay, so be careful. So the data must already be tagged with classes. So it's also can help with dimensionality reduction, okay? And its goal is to what? Maximize class separability, okay? And we already discussed, is it like SVM is trying to use what? Use large margin, is it? Also to separate a class, is it? But today we will see LDA, it's try to make a class separability from a different approach, okay? And also for nonlinear dimensionality reduction, then we can also use the kernel trick. So there is also a kernel PCA, okay, kernel version of PCA for nonlinear dimensionality reduction. Okay, so that's the concept. That's the concept part, is it? Yes. Okay, and the first one we will go over is about PCA. So it's called principal component. So later on, we will see basically it involves a concept called principal component. Basically here, the component is just some vector. Okay, so we will need to find that principal vector, okay? And it's unsupervised, okay? And it says it uses what? It uses orthogonal transformation. And later on, we will see the math behind it, okay? To convert our samples, but those samples, so our data set, samples, they probably correlated. Is it they probably correlated, so some of the features, is it? So over here, this principal component, the goal is to what? Is to convert those maybe correlated variables into a set of values linearly uncorrelated. Okay, then this is called principal component. Okay, so it's orthogonal, is it? So then it's uncorrelated. Okay, in the math behind it, we will see that. And the feature selection previously in the unit, but we didn't discuss in detail because like sequential backward selection, is it? But for those, they maintain original features. Okay, and over here for this one, PCA is going to transform, okay, into new feature space. Okay, new feature space. Okay, so and previously we also discussed is that PCA can also be used for data compression. Okay, to improve storage space and computational efficiency. Okay, it can also work for reduce the curse of dimensionality. Okay, so that's about the general, very general idea. So next, let's take a look the math background behind the PCA. Okay. So over here, we just consider two features. Okay, so we only hear two features. So X1, X2, is it? Then we have different data, etc. So we have, so here I mark it like the square, then it's one class, is it? And the circle is another class of sample. And we also have the cross, it's another. So assuming we have three type of class of data, is it? Okay, and if we try to do the classification, Z classification, if you recall, then the goal is to try to find some, if it's linear, then to find a line to provide the best separable feature, etc. Okay, and that's the what we learned before, like with SVM, is it? But over here, we will think about it differently. Okay, so let's take a look. Suppose you have a new coordinate system. Okay, we call it U1 and U2, is it? And it's so kind of you transform your coordinate system, is it? And what here, our goal is we try to maximize samples variance. So variance of samples. Okay, so variance of the sample is what? Is any sample, is it? Minus the mean, is it? And then you square it. You add all of them together, is it? And you divide by the total number of samples. Is it? This is regarding variance, is it? And then what variance measure? So basically it measures the spread out of data distribution. Is it? So if this value is very large, just think about that means the samples spread out a lot. Is it? It's spread out a lot. So versus like this case and versus these two cases. You compare these two cases. So definitely this one, the variance is very low. And the other case, the variance is very high. So this is quite spread out. Is it? Because you measure, so this is supposed to be the mean. Is it? You measure each sample's distance away from it. And then in this case, here is your X. And then you see it's pretty close. Is it? Okay, so we try to maximize the variance. Is it? Maximize the variance, then it's based on your coordinate system, then it can also be different. Is it? Think about it. Like over here, if we pick this direction, then you can see this is, so the data distributed along this U1 axis the most. Is it? Visually, we can clearly see, is it? Along this axis, it's distribute the most. Is it? So that's the core of PCA. So basically, how do we find this U1 axis? Is it this U1 vector? Okay, so this vector is called principal component. Is it? Because why? Because then the one vertical to it is it's not that spread out. And also when we measure each sample point, they are more close to this U1 axis versus if they are quite far away from U2, the distance. But along this U1 direction, it's spread out the most. Is it? Because along U2, it's just kind of spread out compared with U1, much, much less. Is it? So then in this case, our U1 is a principal component. Okay, principal component. So U1's influence is the most. Okay, so that's the idea behind the principal component. Okay, principal component. Okay, so visually, I think we can understand it. Is it? So let's see the theoretical. So PCA is what attempts to find orthogonal component axis of maximized variance to maximum variance. Okay, so this is the most important. Okay, in our case, that's like what we just discussed. Is it? Previously, you along with X1 and X2. Is it? Now, if we find the U1, is it? Then we reduce it to this dimension. Is it? Reduce from 2 dimension to 1 dimension. Is it? But you keep the spread out feature. that the most spread out feature, so that you won't lose a lot of K influence, okay? And also over here, for the U1 and the U2, why we see U1 is better than U2? Because it's a sample to U1's distance close enough, is it? And we also, the projection on U1, is it? It's separable the best, okay, separable the best. That's why, is it? And if you recall, the distance close enough, is it, with that separable line? That's previously, if you recall, the cost function. Is it a cost function? A lot of time we use that sum of square of error, is it? And sum of the square error we try to minimize, is it? So that's how we said, okay, US isn't close enough, is it? And also along that direction, because it's spread out the most. And if it's spread out the most, definitely it can separate the best. Is it? Otherwise, you just close together, it's hard to separate. But if it's spread out, then it's easy to get different classes, is it? Because each class, they will kind of group together, is it? So it's separable, okay? So visually, we can kind of already get the idea, is it, about principal component. Okay, then in math, okay, machine learning, you can see it's mostly about math. It needs a very advanced math, okay? And so here, another concept we need to understand is about covariance. Okay, so what is covariance here we are going to use? Because we are going to use covariance matrix, okay? It's what? It's about the variance between two features, okay? So this is regarding different feature, okay? So the covariance, then this is the mean, okay? The mean of the samples regarding some feature. Okay, be careful, okay? It's about all samples. Then for each individual feature. Okay, the feature is in your CSV file. That's the column. Is it column 1, column 2, column 3, something, is it? So that's regarding your features, okay? And what this means, this is a mean regarding the features. So basically it's mean of a column, is it? So you're going to take a mean from each column. So that's mu1 and mu j and mu k, okay? And then this is specific sample, is it? So specific sample, so sample 1, sample 2, is it? So sample 1, you have a feature, is it? You have a feature, and that feature's value minus its mean, is it? Time, okay, this same sample, the other feature, is it? And its mean value. Okay, it's mean value. So that's called you times together. Then this is called covariance. And then you add all of them. So this sigma is regarding all samples. Okay, then you can find the covariance between these two basically columns, those two features. Okay, so this is called covariance. Okay, with this covariance, then we can build, because what? We have a number of features. So here, assuming we have D features. D features means D columns. Okay, so D features. And because D features for this covariance, is it for this covariance? Then we are going to have what? We are going to build the covariance matrix. Okay, covariance matrix. So covariance matrix, then it's sigma 1, 1, sigma 1, 2, 2 sigma 1 D, is it? And sigma 2, 1, 2, 2, sigma 2, 3, sigma 2 D, is it? And here it's sigma D1, D2, 2DD, is it? So you write a program to calculate this covariance is not a big deal, is it? So then you can build this covariance matrix. Okay, we call it sigma, is it? Okay, with this covariance matrix, the principal component so this concept basically is regarding that covariance matrix. Okay, that matrix we just saw. Okay, and we try to find, we call it some eigenvalue and eigenvector of this matrix. So this is about eigenvalue and eigenvector. I believe it's your math. Is it some advanced calculus? Is it will discuss the concept? It's quite comprehensive. So we are not to discuss more about eigenvalue and eigenvector. Okay, but anyway. So over here, so regarding that matrix, our goal is to find that eigenvector. So it's not a single one, it's multiple one, okay? Eigenvector, and the eigenvalue is a scalar. So this is a scalar, and this is a vector, okay? So we try to find a vector that can meet this condition, that vector times the covariance matrix, then can also be expressed as a scalar, also times that vector. Okay, so then that vector, we call it eigenvector. Okay, eigenvector, I'm very there are a lot of application with a very, very useful concept, okay? And it says the eigenvectors of the covariance matrix then represents our principal components, okay? So those will represent the direction of maximum variance, okay? And the eigenvalue defines their magnitude. Okay, so that's the math behind it. So over here, generally speaking, how do we pick when we do PCA? We use the total and explain variance to select the number of the eigenvalues and their respective vectors. We are not going to use all of them, okay? So suppose you said, okay, I want to retain 99% of the variance, the original variance. Because after you use the principal components, you pick a certain number of components, then you are not going to have 100% of variance. You will just say, I'm going to pick certain percentage, is it? Suppose 90%. Then the idea is, so this is regarding all features. is it eigenvalues? Because it's 2D, is it all values? And then this is what? This is regarding you're going to pick the top K together, you add them together. And if it's close to 99, then that K number is enough. So you will try, is it 1 or 2 or 3, maybe 10, then you can stop, you reach 99, is it? So that's the idea how we pick the eigenvalue and the eigenvector, okay? And once we have the eigenvector, then the eigenvector will tell you, like in our previous discussion, that U1, and then it may have another U, is it? And another U. So UK, is it? Depends on how you pick, is it? Okay, so that's the idea about eigenvector and eigenvalue. And next, if you recall random forest and the decision tree, is it the feature importance value, is it we can also use that, is it? Is as use class membership information to compute the nodes impurity, is it? That's regarding that. And what variance is a measure what? Measure spread of values along a feature axis, is it? So you can pick out a feature axis, okay? And with the eigenvector, so those are eigenvectors you pick, is it? Then we can build the projection matrix. Okay, the projection matrix, then it's D by K. Okay, because we have D features, is it? And then you pick K eigenvectors, is it? So then you can build this projection matrix. And once we have this projection matrix, then we will be able to transform for each sample, is it? Each sample is 1 by D, is it? Because you have D features onto this new principal component analysis, so PCA's subspace, is it? So we can do this conversion. So this is original sample, so it's 1 times D, is it? And this is the projection matrix, is it? And this projection matrix D by K, is it? That's how you can come up with 1 by K, is it? With this new dimension, is it 1 by K, okay? Okay, so that's regarding how we then project from high dimension to low dimension. Is it? In our very beginning example, we reduce from 2 to 1, is it? So x1, x2 reduce to u1, is it? And u1 is our principal component, okay? Okay, so this is the math background behind the principal component. Okay, and what next is some advice for applying PCA, okay? And you can apply it for compression because we already saw it, is it? Then it can reduce your memory disk, is it? Memory disk to store data. So you can use this. And we can also speed up learning algorithm, is it? And also remember, this is unsupervised. Because it's unsupervised, so that's why we said the data set is unlabeled. Okay, the data set is unlabeled, is it? So here is the example, is that you have a number of samples, is it? Then you apply PCA, then they are going to be reduced to new kind of data set in the reduced dimensionality, reduced feature space, is it? So your new data set is going to be X prime, is it? It's all the projected data. Is it? And after you have this project, you already reduce the feature, is it? Then we can apply some training algorithm. Is it? Later on, we will learn like neural network, okay, or something else, is it? Okay, so this is regarding apply for PCA, okay. And for compression, we can use, it can also be used for visualization because it pick out the important features kind of out. Is it new feature space? Is it more separable? Is it? So visualization, okay. But to be careful, okay, not recommend to prevent overfitting. Okay, to prevent overfitting, we recommend we use what? L2, is it L2 regularization? Is it previously we discussed? Is it? But of course, sometimes if you have too many features, is it? You can also use the feature importance to do the filter out. Okay, and normal recommendation is we try running with original data, raw data, is it? If the result doesn't do what we expect, then we can consider PCA for transformation, okay? To see, because sometimes you have features that are correlated, is it? Correlated, is it? And if you do PCA, then it's uncorrelated. Is it uncorrelated? So sometimes then it helps. Okay. Okay, so this is a theoretical background for PCA. And then next, let's see the LDA. Okay, so this is called linear discriminant. Okay, discriminant. And this is for supervised. Later on, we will see why it says supervised. So it's try to find some feature space that can optimize class separability. So that's the goal. Okay. Be careful, the goal is different between PCA and LDA. LDA is to optimize class separability. PCA is what? Find the orthogonal component. Okay, that orthogonal component going to maximize the variance. Maximize variance means what? You find the most spread out. So visually, okay, we can see, is it most spread out? Because if you have data distributed like this, is it? And if you pick some axis like this, then it's not that spread out when you do the projection, is it? So that's what we care the most regarding PCA, okay? And for LDA, it's linear transformation, okay? This can still be used to reduce number of dimensions, okay? Then let's see. This is supervised. So like over here, it's clearly visualization, we can see it's two classes of data. Is it? Maybe this is the original X1 and the X2. Is it? Maybe that's the original feature space. Then for the original space, feature space, we can clearly say it's not that separable, is it? Because a lot of data, is it, from the cross also projected to what? To interlived with the circle ones, is it? It's not separable, easily separable, is it? Okay, then if you can find like this one, this axis, and for this axis, then when you do the projection, then you can clearly separable these two class of data, is it? But of course, if you project this is really bad, that's not separable. But if you project to this axis, then it's separable, is it? So then the question is, how do we find this axis, is it? But so this is what we discuss as linear discriminant. Analysis, is it? But there are some precondition is data is normally distributed. Okay, so it's going to be normal distribution. Okay, for each class of data. Okay, for each class of data. So it's normally distributed. Okay, that's going to apply. Okay, then. And because over here, we will say it's involves within class and cross-class scattered matrix, okay? So it's involved class. Then over here, that's for each class, we also need to compute the D is still regarding features, okay? D-dimensional mean vector, okay, for each of the class, okay, for each class, assuming here we have C different class, then for each class, you will have one. For each class, you will have one, is it? So for each class, then we need to compute their D-dimensional mean vector. Okay, so that's what we represent as this M. So this MI basically represents for each class, then we compute its mean vector. Okay, the mean vector. So that's regarding the mean vector, and then so that's for each class we have, is it? Then we need to find the within class scatter matrix. We call it SW. So SW is what? You add for all of the class together. But for each class, then it's the sample minus that mean for each of the class. Okay. So anyway, it's given like this. Then it's over all of the class. Okay, this is over all of the class. Okay, so this is within class. Clearly, we can see this is within the class, is it? And we also consider another one, we call it between class scatter matrix. So this is SB. Why? Because this M is overall mean for all samples. This MI, if you recall, it's regarding each class. So each class overall, so that's why we said this is regarding between class. And this is within that class, okay? And then what we need to find is we need to solve the generalized eigenvalue problem for the inverse of SW times SB, okay? The in class and the between class times together. This matrix. special sigma matrix's eigenvalue problem. Okay, and it also said number of linear discriminants is at most C minus 1. Okay, C is a number of classes. So if you have 3, then at most you can have 2. Okay, so this is a math behind it. So once we have this matrix, then the idea is similar as PCA, etc. Then you can find the eigenvalue, eigenvector. Once you find the eigenvector, then you can do the projection, etc. So then you have new feature space. Okay. For the kernel one, today we run out of time. So after break, we will continue to discuss this. Okay. Any other questions? If there is no question, I will see you all after break. Okay. Bye.